which is what number is it? That's more or less what it is. What is that, the price of the
sauce? And 2 different types of juices, frozen or
for only 1 year though?
With 8 months of
So we'll show the price of fruit.
is that my or
No, I tried to pull it down. I think it's just the price of fruit. I don't think it's like there's no time.
You're looking at that.
Do we have any settings yet?
Look right at fruit. Look at 2017. 15%. That's when we started.
Oh, that's right.
That's only
Okay, yes, I agree.
15 wasn't better than that. That was the high school.
Oh, Jesus. I've been out, I hadn't been in high school for 6 years.
Jake's just like, there's a lot of shattering around here. How old are you?
I turned 27.
Wait,
3 months.
December? No, January, whenever that is. December.
January maybe. Like a month.
I like making fun of Kristen because she's older than me. Keep calling her old. Right, we are actually old compared to you. Like Kristen's.
It's not jokes when I say it, it's reality.
I asked. It was a query, not
I've been back my hair. I went to
Okay, let's get started. So a few announcements first. So we are doing the homework lab tomorrow instead of today, and this is because Wednesday's homework is a little bit longer. Thanks. We wanted to, at least give you guys a chance not to have to start right away. That being said, it is a 2-week homework for a reason. It's a long homework. It's probably even longer than the last one. So this one, you guys definitely don't want to wait till the last minute. I don't mean to scare you. I'm just saying that because, if with the past homeworks you've been getting away with starting a little later, this one, the thing is there's several components to it. There's a map, there's a graph, they're linked. Sorry, not a map, a table, a tree. So yeah, definitely get a head start on that. We will do homework lab for that tomorrow. This homework, it's due in 3 weeks technically, but we call it a 2-week homework because we don't assume that you're going to be working on it over fall break. So if you do find that you're needing that extra time, you have it. There was no reason to make it due before fall break. But if you get it done before, obviously you're not stuck with D3 during that week. So that would be nice. Anybody look at it yet? Not a single hand, one hand in the back. Okay, a few hands. Anyone start it? Same hands. Anyone finish it? No hands, okay. Great, so that's the status on homework 5, and then homework 6, and then you guys are gonna, then we're done with homeworks, and then you guys start with the projects, which is really fun as well. So that's the homework load coming your way. Today we're gonna talk about layouts. I forgot to update that title. It's not layouts and maps, obviously we talked about maps last lecture. I'm going to start off with a few things that you need to know, like asynchronous data loading and promises. I'm going to cover them pretty briefly. Alex is going to go into more detail on them in a lecture in the future. So we're going to kind of go through that pretty quickly, and then we're going to dive into the world of layouts, which can get pretty cool. We're going to start off with a simple pie chart, donut chart kind of thing, and end up with some pretty cool force layouts. So let's get started. So you guys have seen this in homeworks already, but I wanted to formally introduce the concept of asynchronous data loading. As the name implies, it means it's not done instantaneously. So asynchronous anything really is usually, when it comes to web development, is usually related to reading files in and out, accessing databases, anything that your computer cannot guarantee is going to happen right away. So we have to deal with that as a special case, because if we don't have the data right away, we need to wait for the data before we can do X, Y, Z. You guys have already seen d3.csv in some of your homeworks, d3.json. Those are all asynchronous data calls. In other words, you have to wait for the data to come in before you can use anything. So let's look at this super straightforward example, and I want to ask, what is the order in which these console.log statements show up on the screen? So we have the first one that says console.log hello. Then we're going to use d3.json to make an asynchronous request for this mydata.json, which lives on our server. Okay? So this is not defined in the script. This is not a variable called mydata.json. It's a file. It's a separate file that lives together with where your website is hosted. Inside that d3.json, we do a console.log. We're done plotting, because you're assuming you've done all the plotting in there. And then when we're done, outside of it is called console.log world. Now, given what I just told you about the concept of d3.json or asynchronous calls in general, I want to ask the order in which these things are going to print out to the console. Either it's going to be the order that's printed there, hello, done plotting, and then world, or it's going to be hello, world, and then done plotting, okay? So I want a show of hands, who thinks it's going to be hello, done plotting, world? One person. 2. 1.5. Who thinks it's the other one?
Depends on how big that file is actually to read.
Yes. We're in a third opinion.
Given the fact that it's a huge file. Okay, so the correct answer is the second one, where if it's big enough, in other words, if it doesn't take a microsecond to evaluate, then we're going to see hello first, then we're going to see world, then we're going to see mydata.json. Okay? And like I said, the reason for that is because it's asynchronous, and so it doesn't necessarily, it evaluates in that order, but it doesn't wait for d3.json to return before continuing to evaluate. And a little bit further on today, we're going to talk about the concept of using a wait to kind of force halt the program until something returns before you continue. But in this setup, that's the order in which things are going to be evaluated. So like I said before, they're usually related to downloading things, reading files in and out, and talking to database. So what this means, and even though this may seem very obvious, I do want to point that out. Yeah, go ahead.
What is the daughter sign for d3.json?
Oh, that's just you don't use that in your code. That was just my syntax thing. You can ignore that. No. So if you have code, and like I was saying, this is something that people will run into and not really realize what's happening. So even though this may seem painfully obvious, I'm going to take the 30 seconds it takes to say it, which is because you only have access to the data inside the d3.json call, you need to make sure that everything that depends on the data, such as plotting, only happens inside your d3.json call. So if you were to, for example, put in d3.json, and let's suppose you have a global variable called all my data, and you say, that's fine, I'll save it in this global variable so that all my functions can access it. So if we had a global called all my data, and in here we set data, all my data equals data, would that mean that this would have access to it when it got to this part of the code? Given the fact if a big enough file takes long enough, it wouldn't, right? Because it didn't have a chance to even populate that global variable before getting to that. So pretty straightforward, but we'll save you a few bugs if you understand why that is. So the idea of asynchronous is very closely related to the idea of promises. So who here has heard of promises? Okay, so a few people. So the idea is that it's a pattern that helps you deal with asynchronous functions, and it returns a single result asynchronously, meaning it'll only return it once you actually have the file or the data from the database or whatever it was. So in the d3.json call, we saw that the way of circumventing it was actually putting the callback inside the function. So if you look at this example here, we have an asynchronous function. You have an argument 1 and argument 2, and then we have this third argument, which is actually a function itself. So what's happening here is we're not using promises yet. We're using giving it one argument and giving it another argument, and only when it receives the callback will it actually evaluate. When it receives the data, will evaluate the function result and do a console.log of result. Result is what's being passed into that third parameter, okay? So say my asynchronous function does a call to a database, and argument 1 is the name of the column that I want, and argument 2 is the name of the number of the row that I want. Asynchronous function is going to go make that database call, and when it returns, it passes that result in to that third function, to that third parameter, which is a function, and then you do a console.log, okay? So that seems to work, and especially on a small scale where you just have one callback dependent on one asynchronous function. But what if you have a series of asynchronous functions, and all of them depend on each other? So let's suppose you're using an API where you want to get all the information, say, for GitHub for a certain user. The first call you need to make is to find that user ID. Then once you have it, you get their account. Once you have their account, you want their top project, and so forth and so forth. Every call depends on the last. You can't make them separately, because you need the information from the previous one to make the next one. And in a situation like that, you have what these are nested callbacks, and that is what is known as callback hell. Okay, because as you can imagine, that gets pretty big. And this one doesn't even deal with the errors. If you have to catch each one of these errors, they show up here, try this, try that, catch that. It gets really big, really ugly, really fast. So this is where promises come into play. I'm going to show you how a promise approach would fix that solution, the callback hell that we just looked at. So here we have task 1 is equal to that asynchronous call, and task 2 says, when you're done with task 1, then call task 2. Task 3 says when you're done with task 2, then call task 3. So the .then is the operator that we use on promises to say, when you return, do this. So syntactically, it makes more sense, it's cleaner, and it is one of the two callbacks that you can do on the promise object. Okay? So now it is up to your async1 function to return what we call a promise. And that promise has a .then, and you can concatenate it just like what we showed there in this very simple example. You can also use this, so you can have a .then, and you can also have a .catch, which is how you would deal with the errors. Okay, and you can, because the errors propagate as you're chaining them, you can actually handle all of them inside this single task3.catch. Okay, you could also nest the call, these two asynchronous calls, inside async1, so it would look like this. Async1 is this function, and then when it's done, call async2, call async3, and catch the error, all inside this async1 call. Okay? Promises can have different states. A promise can be fulfilled, pretty much is the best case scenario. I've returned your data. Rejected, something happened, the database was down, you couldn't find the file, whatever it is. Pending, so it hasn't been either fulfilled or rejected, it's still trying, the file's too large. And settled is just a status, it's kind of a higher level, whether it's been fulfilled or rejected. It's the opposite of pending. Okay? So, if we were to use an async with a promise, then this function here returns a promise. So this is just, honestly, it's another example that shows a slightly even simpler example than the one we saw above. A .then means we're going to call this function as soon as this returns, and if there's anything wrong, we're going to handle it there. Okay? The promise .then, in the examples that I've shown you so far, I've only shown you one input. It can actually take two inputs. One is for a success case, and one is for a failure case. These are optional, you don't have to, but if you do, then this would be the syntax. Okay? Given a promise, when it returns, if it returns favorably, do this. And the second, by default, the second parameter, if it fails, do that. Okay? And that's like a super quick what promises are. Obviously there's a lot on this topic out there, and Alex is going to cover it briefly.
What if you only want to do the error? What if you don't want to do anything on
You just
the
pass in null as the first argument.
Okay.
Yeah, the idea being it's the position that dictates if it's
Okay.
first or second. Okay? ES6 introduced a new concept, which is this await. When you define a function as asynchronously, you have the ability, to what we were saying before, literally saying, wait, don't do anything else until this returns. Okay? So this is the definition of an asynchronous function. So here we're going to get the first user. So what we're going to do, and the try catch here is an alternative to what we had here with the .then, where we could handle a positive result and a negative result. So here we're saying try to get users and then return the first one. If not, we return this default users. Notice that this line right here makes the program get there, and it literally sits there until get users returns, puts the result in users, we then have the user zero.name, and it returns. If we didn't have the await there, then we wouldn't have the result, and this would be an error, user zero.name. Okay? So await is a nice short syntax, and it forces the code to be as sequential as you would expect to see it written on your screen. So this is something that, especially since CS6 came out and people have been using it, is a really nice feature. Okay, so one thing to notice is because we use the async, doesn't mean that it's automatically going to, sorry, let me just finish this sentence, await. You actually have to write in the await, because if you don't, even though this will not throw an error, what this returns is a promise, which you then have to use the .then syntax and so forth and so on. But if you don't use the await here and then you try this, that's going to give you an error because user 0, it's a promise, right? Users is a promise, so there is no user 0. Users is not an array, it's not an actual result. Yep.
So in this example over here, is getUsers an asynchronous method or not?
It is an asynchronous method in the sense that it makes an asynchronous call, but it will actually wait. So the fact that you're waiting doesn't make it not asynchronous, right? It just means there is something here that's going to take a while. Whether you handle it with an await, meaning you stop the code, or you handle it with a promise and a then is your choice. It's only indicating that it will take time.
Okay. So basically any function in your program, you can just use await and then make it asynchronous.
Yes,
Okay.
absolutely. Okay, so that just wanted to point out that you do have to use the await if you want the code to stop. Otherwise, the default behavior is that it's going to return a promise and you handle it like we saw before. Okay? And the most important thing, not the most important thing now that I mention it, an important thing is that hopefully it's become clear that async await are really just different ways of handling promises. They're promises under the hood. It's just actually waiting, but they both handle exactly the same thing. Yeah.
So you said await is ES6 JavaScript.
Yeah.
Are promises also JavaScript, or is that?
Promises are not ES6, but they are JavaScript. They've been available since before ES6.
Oh, okay.
Yeah. So the await wrapper is a new thing that kind of puts a sugar coating on top of promises. Yeah. Okay, so that was our 15. Yep.
Wait, so if you do it the promise way without the await, the other part of the code will keep going,
Yes.
right?
And then you have to use the .then to
Yeah.
enforce, kind of like we did here before, and say when that returns, then do the rest of the code.
Okay.
Yeah.
So is that preferable because you're not stopping execution of other things that don't depend on the promise?
I think because it's kind of what we were saying, this idea of asynchronous really is seconds or milliseconds. I think it depends on how long you think your thing's going to take,
Okay.
right? Honestly, in my code, I've used it with the latest stuff. I use a lot of await, and that really never took long enough to feel, and I felt like it was a nice syntax thing, and it really made sense to me. But if you're making a database call, it can take really long. Of course, the fact that even if you use the .then, you still don't have the data until it comes back, right? So you're going to have a blank page, for example, or whatever relies on that data.
But I mean, other code could be
Yes,
executing.
depending on what your
later.
other code does, yes,
Okay.
absolutely. And Alex, feel free to, if there's anything else you want to add to that.
It's absolutely the right answer. This is essentially fake parallelism.
Okay, so we're done with promises. You've heard of it. That's pretty much the intent of those first 15 minutes, and we're going to talk about it more in later lectures. Now we're going to get into layouts. And this is one of those lectures that you don't necessarily obviously have to code along. If you have your computer up, it's really nice because we're going to be playing around with it. And that's one of the really nice things about this setup for the lectures is that we are going to play around with the code and see how that updates our final layout. And that's really fun to do. So if you want to play along on your computer, feel free. Otherwise, you can just follow along what we're doing here. So before we even dig into the code, one thing I want to make clear is this concept of D3 functions that manipulate the data versus D3 functions that give you layout. And by layout, I mean positions on the screen, okay? And throughout all of our examples, we're going to be distinguishing between, am I wrangling my data into a format that makes sense for this layout? Or am I getting X, Y positions that I will then use with my nodes with my SVG enter append to actual position, okay? And that's an important distinction so that you understand what you're doing when you go ahead and code some of these up yourself. I'm going to start with the most simple one ever, which are pie charts, which get a bad rap. Look at them anyway because they're a great introduction to layouts, and sometimes they can be used appropriately. So there are two things that we're going to look at here, d3.py and d3.arc. Can anyone guess which one is the one that manipulates the data and which is the one that gives you actual locations on the screen, just based on those names? Just a guess, I don't care, just say a random one.
arc works with data and pi does the layout?
It's the opposite, but thank you for speaking up. So an arc is literally like a drawing, right? If you think of like a compass or something, you're drawing an arc. So the arc is the one that's going to give us the positions on the screen, and pi is the one that is going to actually do the math and tell us what the angle is and all the things that we will then use to draw it on the screen, okay? So we're going to start just looking at this very simple pi equals d3.pi data. I don't know why that's formatted funny. That's supposed to link to the actual README. When you guys are going through, I mean, I've put a pretty summarized version of each layout here. I highly recommend that you go to the D3 API. A lot of examples, really well documented, and I couldn't possibly state all of the possible variations, but these layouts, you can do so much with them. You can change the angle that the wedges are on Tuesdays versus Thursdays. I mean, there is an infinite number of things you can tweak. So I'm just really showing you a few to give you a taste of how much you can control something as simple as a pie chart or something as complex as a force node link diagram. Okay, so like we just said, the call to d3.pi doesn't produce the actual shape, but it computes the angles for you for each wedge and how we're going to put them on the screen. Okay, so the data that we output, so this is a data wrangling function, will then be used inside d3.arc to draw the actual path generator, draw the actual arcs, and so this is a path generator. Produces a circular SVG shape. Okay, so if we look at the output of what d3.pi data gives us, for each element that we feed in, it returns back the data element, the index, so if you have 5 elements, it's the counter of 1, 2, 3, 4, 5, the value of the arc, start angle, end angle, and padding angle. And we'll take a closer look to see what those means. One thing that I do want to point out, especially if you're playing with your own values, is this concept of what is the value of the arc. A lot of times people think arcs, they think degrees. In D3, and I don't know if you can actually change that, I'm sure you can, we're looking at radians. Okay, so it's actually the distance of the arc itself. That's what the value is. So let's step through this code and play around with it to see how we can change it. So here we have a super simple data structure, right? It's an array, and each one of the objects has an operating system and a market share. Here we're just setting up the basics, the width and the height, selecting the SVG. You guys have done this a million times by now. We have a ordinal scale. So we have as many colors as we have operating systems. And then we're going to start by creating this layout generator here, so the d3.pi. One of the things that pi takes as a generator is when we say we want to know what the value of each share is, that can mean different things for different objects, right? So this is kind of the idea of when we talk about key functions where you say, I want to associate every data to an SVG according to its name, state name, or whatever. So in this case, we're saying, hey, the share is what our value is. We want each wedge in the pi to be proportional to the share attribute of that object. Okay, and then we'll play around with this so we can see how it changes later, but the idea, first we're going to do the most basic pie chart possible, and then we'll play around with it. Then we pass in our data, our array of data objects into our pi generator, and then here, I hope this isn't too, let me do it clear here. And just like we looked at when I showed you before in the conceptual thing, each one of these, so you have 5, the data that comes back from pi that's been calculated for you. There's the actual data object that we gave in, so it keeps track of that. Then it has a starting angle, an end angle, the index, so this is the first one, a padding angle, which we have not set, but if we do, you'll see what that does, and the actual value of 82.8. Okay? Let's look at another one so you can compare what this start and end angle mean. The first one obviously starts at 0 and ends at 5 degrees. The last one starts at 6.24. Actually, this is probably not degrees then, this is probably radians as well, and ends at 6.28. So this is just so you get an idea of what this would look like with actual data. Now that we have the data in the format that we need, and usually you have a data wrangler associated to an SVG generator, because as you can tell, the SVG generator needs some very specific information, like the angles and start where it ends. So we've done the d3.pi to get the data in that shape, and now we're going to look at the arc to actually draw it out. So this is the path generator, d3.arc. Can someone tell me off the top of their head an example of any other path generator that you've seen before in this class? Just one. A really simple one that you used in like homework 2 probably. Something that outputs positions on the screen. Sorry, say it again?
The path generator?
Yes, the path generator was what we called it. What D3 function did it use?
Line.
Line is one of them, yes. Scale is not, I don't know, I heard scale from here somewhere. It doesn't output an SVG path. It gives you pixels that we use to position SVG elements. D3 area, D3 line, these are all examples. This one, D3 arc, is a step above in complexity, but I want to make clear here is that all of these are functions that take in data and return an SVG path, which is that really obnoxious thing that you guys had to draw in homework 1 by actually doing the pen, excuse me, move and so forth and so on. So this is doing it for you at increasingly complex levels. So we can set all kinds of fun stuff like the outer radius and the inner radius and so forth, and we'll mess around with that to see how that looks. And then what that outputs, so this is the generator, right, the arc. If we give it in a single data element, so remember how our pi data had 5 elements? If we just give in one just to kind of see what it outputs, this is the output of the arc, M1, so this is the path that you don't have to write because this path generator is doing it for you, right there. So now we have our SVG data, or the paths for our SVG. We have the actual data that we want to associate to each wedge. So here we're doing the very standard at this point. You select a group, you give in the data, you enter and append. Now one thing that may be painfully obvious, but honestly when you're starting off with D3 may not be super clear, why are we giving pi data as the data associated to the pi, as opposed to the SVG output of the arc generator? So we have 2 different outputs here, right? One is this data that's been formatted that has angles and start angle, end angle and data, and the other is this path, right? What do we want to associate to each wedge in our pie chart? Do we want to associate a path or do we want to associate a data element? Data element, right? And pi data, even though it's been manipulated and calculated, still has that original data that we gave it, right? So if we want to color these wedges, we still need access to that data. If we want to put a text label, which we will, we also need access to that data. So I just want to make it clear the process here from that original very boring array of objects just had 2 things. It got a whole bunch of stuff calculated with d3.py. We're still appending these objects as our data that associates to each one. The SVG path is only used down here to draw it. Okay? Just want to make that clear, the distinction between the SVG path and the data associated to each path. And stop me if this doesn't make sense. And so like I said, we actually want to use the data to color it. So here we're doing a style where the fill is a function of d.data.os. Notice that we have a .data here because when the d3.py generator wrangled all the data for us, it kept our original data objects in a .data attribute. Okay? Same thing here, we're going to use that data again to create a label, and then we're going to move things around. One of the cool things here, cool may be a strong word, one of the things here is that arc has, one of the many functions that arc gives you is the centroid. And the centroid is pretty much given an arc where it is right in the middle here. And the reason that it's made for labeling is because I'll show you is that as we make this into a donut chart, where we get, and it will move the label accordingly to be in the middle of only the visible part. So this is something that's made specifically for labeling, and there we have the most uninspiring pie chart ever. So I just want to play around a little bit with some of the features so you can see. So let's suppose we come up here and we change the start angle. So if you notice, it rotated it, so it's no longer starting at 0. But now we're going to change the end angle as well, so it's not at 360 degrees. So it's just half. And then maybe we want to add some space in between the wedges. So there's something called padding. So we're going to add that. Sorry, I have to keep scrolling. And then maybe we want to round the edges a little bit because they look really harsh. And then we come up here and much nicer pie chart. Proof of concept, just to say, once you generate your basic shape, you can do all kinds of stuff to it and change it, and then you can maybe do a hover, and then you would actually see all the data associated with it, and so forth. Okay? Well, I'm going to skip through this. This is pretty much stuff that we've already talked about in detail. And now we're going to jump into slightly more complex layouts. And I went pretty slowly through the pie stuff to make these concepts very clear, because as you can imagine, as we get into more complex layouts, the structure of the data also gets more complex. But if you understand this idea of what's data, what's a path, what generates data, what generates paths, it becomes much easier to follow. So the next one that we're going to look at is called a chord layout. Now, before I show you what the chord layout looks like, has anyone seen one of these before? Once I show you, you might recognize it, because this is what a chord layout looks like. Okay, so we went from a not so interesting pie chart to a pretty cool chord diagram. And then when we finish this, I'm going to show you something really cool that a blogger that's really prolific in the D3 world called Nadia Bremer, she actually gave the talk in the D3 conference that I was at this past week. And she does some really cool stuff, so I'll show you that. Oh, one thing I didn't show you for the pie that actually becomes relevant for the chord layout is this idea of an inner radius. So it goes from a pie chart to a donut chart. Well, it would if we had the whole thing. Let's make that let's comment that out, and let's make our inner radius 200. That's really big. This is the thing that I was saying, right? So the centroid actually puts it in the middle no matter how big your wedge is, which is pretty useful. Okay, so the idea with the chord layout is the initial data is a matrix. So think of, you have all of your elements as columns, all of your columns, all of the elements as rows, and the flow from one to the other is if you pretty much follow in where they meet in the matrix, right? So it'll make a little bit more sense when we actually look at how the data is represented here. So the example that we're gonna go through is based on this super simple, so you have a matrix of 4 rows, 4 columns, and this is the data that you have. So you're pretty much interested in how every I relates to every J. The 3 D3 functions that we're gonna look at here, make this a little bit bigger, is D3.chord, arc, and ribbon. And this is where, again, it becomes very important to understand the distinction between what are the ones that are generating data and the ones that are generating the SVG path. So here we have D3.chord, which is analogous to our D3.py. It's going to get our data and it's going to put it in the format that our layout needs. Okay? Usually, what I think might be not super intuitive when you first think about it, these D3 functions that are named after the final layout don't actually give you the layout. They give you the data in the right form for the layout. So, for example, before I actually go into the other two, if you look at this, you see two types of SVG paths here. One is the arcs that look a lot like the pie chart that we just looked at, right? These circular arcs, they just have an inner radius, so this would be like a donut chart. And then you have these, what D3 calls ribbons, that connects them. So instead of having a whole new SVG generator for chord diagrams, we're going to be using the ribbons and the arc and the arc, I'm going to say that wrong, together to generate this. So we have this generates the data we need, and then we're going to use a combination of D3.arc and D3.ribbon to generate the 2 separate paths. Okay? So when you run, like when we put the data through D3.py, you'll remember that we had these 5 elements that had the data and then had the angles and all the things that we needed. So if we take a closer look at what D3.chord returns, it returns 2 things. One is an array of chords. So each one of them is one of what we're going to use in our ribbons. And they represent the bidirectional flow between 2 nodes, I and J, in our original data matrix. And it's an object, and we'll look at this in the console.log in a bit, that has both a source and a target. So think of it as these links, right, that go from our source group to our target group. Each one of these subgroups has a start angle, an end angle, a value, an index, and a subindex. And so you'll see this looks a lot like the data that we fed in to create the pie chart. The data from these chords we're going to pass into D3.ribbon, and we're going to display these network relationships with these ribbons. Other than that, our D3.chord also returns a secondary array called chord.groups, and each one of these groups represent the combined outflow for each node And again, when we look at the console, it'll be a little bit more clear how we use this to draw it. And it has a start angle and angle, a value and index. And this looks exactly like what we passed in from d3.py into our arc generator. So the output of chord.nodes, we pass into d3.arc, and we produce this donut chart around these ribbons. So let's step through this example kind of like we did with the pi and see how this works and what we can do to change it up. So a very straightforward, just like from the example before, a matrix of values, selecting our SVGs. And here, we define these two as, it's funny, it's a little offset the highlighting, as constants because we use them for both SVG generators. We're going to use them both to generate this donut around the chord diagram, and we're also going to use it to say, for these ribbons, how big do we want them? This is just a D3 format for the labels. And then this is the equivalent, right, to d3.py. So we create the data and we give it a padding angle of 0.05, and we'll change that later to see what that does. And then here, this is very similar, exactly like what we did above, where we want a path generator for an arc, and we give it both an inner radius and an outer radius. We started the pi with a 0 inner radius. Here, we're already starting with a given radius so that we get just the donut and not an entire circle that covers everything. Okay? So now we have the call to, let me see if I put something down here. No. Let's see how d3.ribbon So this is the one that's going to generate the paths for those beautiful things in the middle called ribbons, and it takes in a radius. Now notice here that we define the radius, the inner radius. The same thing that we give as the inner radius to the ribbon is what we give to the inner radius to the donut. What would happen if those two values were different?
The ribbons might go to the inside of the donut.
They would either, if it's too big, go into the donut, or if it's too small, they'd be in the middle. So let's change that just for fun. So right now, the ribbons end exactly where the donut starts, right? And I believe our inner radius value is, our radius minus 30. Totally know what that means. And so we're going to change this to 100. Oops. We get this tiny little thing in the middle, right? So you, one second. So you have full control over how big it is, but obviously your layout doesn't look as nice if it doesn't match up exactly the radius of one with the inner radius of the other. Yes?
Could you explain the matrix data structure? The data for the pie chart is the first row or first column?
So I understood up until you asked me to explain this data. What were you saying about the pie chart?
Yeah, the other side is something like a donut chart.
Yes.
So this data comes from the first row or first column.
Oh, okay, okay. Let me just set this back to, so that we can. So the idea here is that you have 1, 2, 3, 4. Well, actually, let me start off with the starting from the matrix to how we end up here. Think of a very simple matrix with 3 rows and 3 columns. And we want to know how does the data flow from one to the other. And that value is found at the intersection of that I and that j. Okay? So if we had, and it becomes even more clear in the Lord of the Rings example, because there's an interpretation to what it means, flow from one to the other. But the idea is that we then take this idea of the value of the flow between two elements and draw it as a ribbon that connects these two elements. So one is I and the other one is j. But, well, why don't I finish the chord stuff, and then if it's still not clear, we'll come back to that. Is that okay?
I understand the ribbon. I mean, for most other side of the percent.
You mean these groups here?
The donut chart value, the percent value, or the angle value come
from the groups. From these groups, and when we look at the data in the console, you'll see where that comes from. You're asking what is the value that goes into making these donut Yeah, when we look at the console.log of the data, it'll be a little more clear where that comes from. So we stopped here. So now we have a ribbon that is the same radius as the arc. We have this color scale. And now, if we look at the data, so we called Chord, which is the one that does the data wrangling, on our original very simple matrix, right? And we want to see what that looks like. So we have two things. One is we have 9 different ribbons, and each one of them has a source and a target. And this is and it calculates for you the starting angle and the end angle so that the ribbons can actually be drawn. Other than that, we also have this array of groups. And this is the data that's going to feed into the donut chart. Okay? So notice that we have 1, 2, 3, 4, which is the same number of segments in our donut chart. And each one of these has a start angle and an end angle, which defines where they start and where they end. So if we give this a padding, it would change the look of the donut. So it is one of the outputs of the Chord, the d3.chord data wrangler. Do not ask me that under. I have no idea how it calculates it. You want to know what is the math that ends up with the start angle and the end angle? I don't know. But all of this is open source. So if you go into d3.chord, you can see exactly what it does. Yeah. So now that we know what data is associated to what part, we're going to create a group. And this is something that brings up something I talked about last lecture. I'm interested if anyone remembers this. I think you asked me the difference, or someone up here asked me the difference between data and datum. And we're using datum here, and we're using data here. And this is important. And I was wondering if anyone remembers the difference.
The data is just 1 point, and then
Which one is just 1 point?
datum.
Yes, exactly. So what datum is saying, I don't care if this is an array. I don't care how much, I want to associate all of this data to one element in the DOM, whether it's an SVG, a group, or a path, or a div, or whatever. If you recall, the concept behind D3 is if you have an array of data and you do a dot data, it will create 1 SVG per element in your array, right? So what we're saying here is take everything in this array and associate it to one element. And we're doing this because we want this parent group here to have all of the data associated to it. So we're binding all of our different chords to this one group, which we will then pass on to the subgroups, as you'll see. But that's why we use .data. If we use a .data there, we would have as many groups as we have elements in our chord, which would be 9. Okay? So, and this is another thing that I don't think we've actually, I don't recall if we've seen, which is this idea of passing down data from parent to child. And so you'll notice here, see this call to .data? It doesn't actually have any data, it just has a function. Okay? And this syntax means take the parent data and give me back, in this case it's returning chord.groups. Okay? So what we're doing here is saying get this master group that has all of the data appended to this single group. Now select all G. So we are now creating a subset of G's, one for each data in that element, and then for each one, our data is going to be a subset of that. So in this case, we only care about chords.group. Okay, we don't care about any of the other things because right now we're just generating the pie, the donut part of the chart. And then for each one of those, we're going to append a group and draw the path with the arc, which is the path generator.
What's chords.groups?
So chords.group, if you recall from here, is this, right? So the output of chord, d3.chord on the data, gave us two things: 9 separate ribbons and a single array with the donut chart information. So what we're saying is give me all that data, but we only care about chord.groups here, so only give us that to associate to each one of these. So each one of these is now a group. That's a group, that's a group. Okay, so it's associating one group per chunk. We're doing the enter, we're appending the G. Notice that none of these examples, because they really are to exemplify the layouts, use the update and the merge and stuff like that. It only appends stuff to the enter and does the styling. So even though it works, just keep in mind that a lot of times you copy this code to make something more complex, you do need to adjust it so that if your data changes and you want your chord diagram to have more or less arcs, that you need to update your code accordingly. Okay, and the rest is the aesthetics. So I'm going to go through it pretty quickly because we actually still have quite a few layouts to go through. So we're appending, so this is similar to what we've done in the donut chart. We append a path. Notice here that I'm not giving it a .data, right? And this is because our data is already bound in this step. We bound the data to the group and there already is data, so we can just say append a path, and when you draw the arc, when you draw the actual SVG, use our arc generator. Okay? And then here is just the aesthetics of actually drawing these ticks here. So we have a helper function called group ticks that will actually take in the start and the end angle of each wedge, divided up by how many ribbons are in here and create these ticks. And we use those to actually append the text and so forth. And this is really just math and aesthetics. So it doesn't really relate to the actual layout, so we can skip through those. Let me see if there's anything else that I want to. We are styling the ribbons with the data for the target. And there's this cool thing called dot darker, where you can actually get a color and do a dot darker on it so that our stroke is darker than our fill. There's just nice little aesthetic things to make the layout look like this. So before we go into tree layout, I do want to show you this, which I thought was pretty cool, even though I've never read or seen the movies. It's not my thing at all. I still thought it was pretty cool. So this is a slightly fancier, it's still a chord layout. And one nice thing is in her blocks, she actually shows you all the steps on how to, once you have the chord diagram, how to separate them, how to do the wedges bigger or smaller. So this is like the ultimate fancy version of a chord diagram. But the idea here is that you can see how many lines of speech each one of these characters had in each one of these locations. And then she added a nice little snippet of, this is interesting because, at the bottom. So this is a really cool example of a visualization that's made not for exploration, but to kind of tell a story, right? She's already kind of catered, she's already, not the word isn't catered, it's, what does a museum do? Curated, thank you. Curated what she wants to say for each character. And when you hover over it, you get to see, and maybe you can find something else out, I guess it is kind of exploratory, but the idea here is this was very much made to tell the story of how much these characters, whenever she presents this, she always says, and I wish I knew which was the characters, but there was one character that was in all three movies, I think it was this guy, that spoke less than this guy who apparently died in the first movie, and I'm sorry if I ruined it for someone who hasn't seen it. Didn't mean a spoiler alert. If you're watching this video, I'm going to ruin it. Someone dies in the first movie. Okay, now we're going to talk about trees, tree maps, and nodeling diagrams. And depending on how this goes, I might skip to the nodeling diagrams and let you guys do the tree maps. So trees are the super exciting hierarchical data, right? Has this cool little interaction and this is like the default D3 tree, which is funny because I just came back from a few weeks ago, I was at this hackathon back in Boston with some folks at Harvard, and the idea was create a visualization over this data from their API, and a lot of people weren't front-end developers, so they looked up like default ways to do it, and so many people did the tree map or the tree. But if you've done D3 for even just a little bit, you know that this is the blocks super standard default. You got the code, you just put your own data in, which is kind of like the IKEA furniture, you know, where you know exactly what it looks like. Oh, that's IKEA. Well, this is the quintessential D3 tree. So what I want to say about this, and we may not have time to go through all this code in a lot of detail, is this idea that we need to, again, wrangle the data. It starts getting a little bit more complex, right? So now we have data that may or may not already be in hierarchical format, but just like we had d3.py and d3.chord that calculated our angles for us, in this case we're going to use d3.hierarchy, and I know I misspelled this so many places in this. I'm going to have to do a search and replace every time I write it out. It looks weird. to get our data into this format of roots and parents and children and so forth and so on, right? So this step of actually creating a hierarchy that has fields, parent, children, and functions such as get all my ancestors, get all my descendants, can be done one of two ways. So I'm going to show you the D3.hierarchy way with the tree layout, and I'm going to show you the D3.stratify way with the tree map. Now, for those of you who are going to venture into doing the hacker version of Homework 5, you will be using D3.stratify. So, good thing to pay attention to. So, here we're going to take a look at, let's suppose we have this input data, and this is not what we're visualizing down there, but just an idea of what hierarchical data looks like. It's a JSON file, has a name, has children, has a name, has children. And even though this already is in hierarchical format in the sense that you have parents and children, it doesn't have all of the attributes that our layout is going to need, such as parent, parent ID, and so forth. So we still need to run it through D3.hierarchy. Okay, and this is what that line of code does. Pretty straightforward. Here's the data, create a hierarchy for me. And this children is optional because maybe your children attribute isn't called children. So it defaults to, it will know that it's the children if it's called children, which our data, I just said children like 5 million times. It's called this in our data, but if maybe you had any other word, this is where you would do function D, return D dot, whatever the name of that attribute was. So this concept of having an accessor function, as you can see, is prevalent all over D3. When we want to do a fill according to an attribute, when we want to do a key, and all of these things have this second optional argument that says, hey, of my data object, return this attribute for whatever I'm doing here in the beginning. So this is very similar. So when you return from this D3.hierarchy, this root node has data, has depth, has a height, and the height is pretty much this concept. Remember when you guys drew that tree for homework? Who knows what the number was, but there was one. And that we did the level. This is the equivalent of the height, the parent, the children, and the actual value of that node and all of its descendants. Once you get the data into this format, you can use these really cool things, which is .ancestors and .descendants, which, as you might expect, gives you all the nodes above you or all the nodes below you. And we're going to use that both for this one and for the tree map one, so it's pretty kind of a cool thing. And again, like I said, these are just a few of the several things that the tree and the tree map and all these layouts give you, but I've only pointed out the ones that are relevant for this example. Okay? So we've done the data munging part of it, and now we're going to use tree to actually give us the layout, the X positions and the Y positions that we will then use to place our elements on the screen. So this is the smallest tree ever, right? And we have these labels that are very indicative of top level, level 2, and so forth. I'm going to go through this and see what are things worth mentioning. Just the styling stuff. Here there are 3 things that we're going to be using. The duration is the duration of the transition. I is just a counter, and the root is the variable that we are going to, it's going to be returned by D3.hierarchy. So here we have a layout. Even though we don't have any data yet, we created a layout that's pretty much empty, and we just give it a size, but there's no nodes in it yet. We still need to pass in the data, which is eventually going to be root. Okay? Now, so this we've seen, it's pretty much, and this is actually redundant because that's what it defaults to, but I wanted to show you, this is the syntax if it wasn't called d.children, if the attribute for the children wasn't called children. And then these 2 lines, we actually put in there because we're going to use, for the animation, we want that the new nodes to originate at the parent's old position. And you'll see once we animate how that, so this is not part of the mandatory, you don't need to manually set x0 and y0, we just have this second pair of attributes that says, hey, when we animate, where were my parents at before we started animating? Okay, then we go through each one of them and we collapse them, and then we run the update. So the collapse function here, and let me just go back and do the animation again so you know what I'm talking about as far as each of these interactions. So you'll notice that the nodes move around, right, when you animate to accommodate for the height of new nodes. And one thing that happens is that we want the nodes that are either when they're collapsing or when they're expanding to always go as a function of where your parent was or will be. So we have the second pair of relevant positions. That's what's our x0 and y0. Also notice that even though this node in this layout does not have children, we want to keep track of those children because when we click on them, we want them to show up, right? So this concept of hidden children is what we implemented with this what Mike Bostock did in this block. All of these are actually, and we reference them at the top of this file, are examples that have been modified based on Mike Bostock's like standard implementation of each one of these. So, where's our collapse? Here. So this is pretty much the concept, right? This is a recursive call that pretty much says for each one, if we're hiding the children, if we want to collapse, that means we want to hide the children. This underscore children is our hidden children. So we're going to put the children in the hidden children. We're going to set the children to null, and we're going to kind of traverse down that tree so that we don't lose access to them. Okay. Once we've done that, we're able to update, and the update is pretty straightforward. So the nodes is if you get the root of the tree data, of the tree map, and you call that descendants, it'll pretty much give you all of the nodes that are visible in that tree. And then here, because we start off, the first time you load this up, you only want the links to the children that are available, so we only slice out and get the first set of links. This is actually just aligned so that the tree map doesn't take up the whole width every time. So you pretty much just say, what's my maximum width, and size it by that. And then the rest is pretty much code that you guys are probably very familiar with at this point, where we use the data to both position the nodes, append new circles, and so forth. And so this is, for example, where we want new nodes. We don't just want them to show up out of the blue. So all of the enter selection, which is nodes that weren't there before I clicked but now are, first position them at my source y0 and x0, which is where the parent was, and then append it, and then after you put everyone together, you've merged the new nodes with the existing nodes, then you transition them to their due x and y locations. Okay? So none of this, Oh, another nice syntax thing worth pointing out here is this, it's kind of like when we looked at the ternary operator, if this, then that, otherwise this. This is kind of an added layer to that. So it's saying, if you have children, just return that, right? It's the or, A or B. If A is true, you return that and you don't even look at B. If you don't have children, then do you have hidden children? That's the second question. If yes, return end. If not, return start. This is where we're positioning the labels for our nodes. So it's a super, super compact way of checking for if you have children, if you don't have children, and so forth. Same thing here, we're checking for children for where the syntax highlighting of what color. So we make the nodes that do have hidden children light blue so you know where you can click. And we remove exit nodes. Now here's something interesting that actually wasn't entirely clear when I was first going through this, and I thought was interesting to kind of note. Notice this sequence of elements here, right? So we're saying, hey, get all the extra nodes on our screen and remove them. But before we remove them, let's remove them smoothly with this transition that has this duration, and then you're going to slowly translate it, and then you're going to remove it, right? Hopefully this code is very clear to everyone. After we've removed the circle, we then take all of the exit ones and we reduce the size. Doesn't that seem wrong? Does anyone have an idea of why this works? And I'll show you, and we'll just kind of see that in action so you believe me that it works. Look at the size of son A and daughter of A. See how they get really small and then they disappear? But we only set the size to small after we did that remove. I'm going to bring the code back up, and I'm going to give you guys 10 seconds. How long does this take? This highlighting is a bummer, to evaluate. Transition, how long is that transition? Not instantaneous, right? There's a duration to that, which is 750 milliseconds. How long does it take for the code to get from here to here? Less than 750 milliseconds. So what happens is we said, hey, I want you to do this really, really slowly, and before it's done, it's actually going to set the radius to small. So even though the order of the code is completely counterintuitive, because of the transition, if we didn't have the transition, this would make no sense, right? For you to set the radius after you've removed it. But because we're doing it really slowly, we have time to actually reduce the radius and then remove it. No one seems nearly as enthralled with that as I was when I read it. Okay, so then we have the enter, update, exit syntax for the links, which is very similar. And then this is a custom-made SVG path generator. So we've looked at either these super simple line, right, generators, or we've looked at these super complex chord ones that creates angles and all kinds of stuff. We can also create our own, which is you give me data and I will tell you where to draw that path, and this is one of them, okay? So this creates what they call a diagonal, but is this kind of more funky looking link. So if you wanted to make a path that did something really crazy, you can actually create your own path generator, and then in the .path attribute, in the .d attribute D, you call your own custom path generator. Okay, so this is just one other way of outputting an SVG path. You're not restricted to, despite there being several D3's path generators. And that's the tree. Okay, let's go through the tree map layout pretty quickly. The tree map layout, I found a really cool data set, which is the actual D3 library. So this is what, let me make it a little smaller so we can see the whole thing. This is a tree map, okay? And the concept is representing hierarchies as nested boxes. That's pretty much it. And you can use color to create different categories. So in this case, if you'll hover over one of these, you'll be able to see, once I zoom back in, what these categories in this case are. So for example, all of the blue ones are all part of the D3GO library. So these are all of the functions inside the D3GO library. Okay, and then here we have, I think, projections, or I don't know if that was the next one, no, transitions, and so forth. So the idea is you kind of categorize them, and then you draw the map. So this is one big square for D3 projection. Then inside it you have, so this is a very shallow, you're only nesting it by 2. The big square is D3. The smaller squares that are colored differently are the D3GO, D3 transition, and then inside you have the actual functions. Okay? So let's look at how we wrangle the data into this format. It's funny, I have this is not the latest because I have all the text. Let me just do a force refresh here. Okay, there we go. This was before I had to say. So the concept of the tree map layout was introduced by Ben Schneiderman, who's a really big name in data visualization. And it's the concept of subdividing areas into rectangles, right? So this example here has the original code. And so here we're going to use d3.stratify because unlike our example with the tree where we had this hierarchical JSON file, we have something like this. The CSV file is much bigger than this, obviously, but the concept is we have the path, and then we have the size of that file. And I'm not sure if it's kilobytes or lines of code, but it's some value associated to each file. So as you might have thought or imagined or wondered, how big are these squares? It has to be proportional to something, otherwise they'd all be the same size. So in this case, we're making it proportional to this size attribute. Okay? So we're going to use d3.stratify in order to take the CSV and make it into this nested structure of parent, all the children, and the size of each one as you go forth. So similar to d3.hierarchy, we use d3.stratify. We specify both, just like we did with we could specify the children. Here we're specifying the parent ID. So in this case, our data is the parent attribute. And the ID is the actual name, and that returns, ooh, this is too big, a root to this tree that we've just created. And every root has an array of all its children, the actual data object still appended to it, the depth of where you are in this hierarchy, an ID, which we just specified here as to what is the attribute that we want to use as an ID, and because it's the root in this case, the parent is null. So once we have this hierarchical data structure, we can feed it into d3.treemap to get our actual layout positions. So just like d3.tree, just like d3.arc, just like all these others that generate positions on the screen, d3.treemap returns X and Y positions for our nodes. Now, unlike the tree, this doesn't just have an X and Y position because each element is a box, and a box needs a start and an end position. So which is why we have X0 and X1, which is the left edge of the rectangle, the top, the right edge, and the bottom. Now, one quick note, and this is a very common bug that people don't notice, is that once you've calculated the root, you actually need to go and run root.sum. And as you might imagine, root.sum is pretty much going to sum all of the children and give you a certain value. Why do you think we need to run root.sum if you think about what I just said about the size of the boxes? If you think about a leaf node at the very end, the data that we're looking at, the CSV, every file has a size. But we're drawing these rectangles to encompass a whole bunch of files, and then a bigger rectangle. So the big D3 rectangle needs to have a size. So what you need to do is sum up the value of all of the children, right? Otherwise, we would only have values associated to the leaves. And the whole concept is we want to hierarchically build rectangles that enclose other rectangles that enclose other rectangles. So at each level of the tree, I want to know, sum up of all my children, what is the size of this rectangle? And then when you go down one more level until you get to the actual leaf, which is a tiny little rectangle depending on how many levels you have, okay? So even though that's not really part of the required, as far as like, it's not like if you don't give it an X or a Y, it doesn't know where to plot it. If you don't give it a sum, it doesn't have a value to size your rectangle by. So here we do just create this base tree map generator. It doesn't have any data yet. These are just used to create the links back to the original, because if you click on any of those rectangles, it'll actually take you to the documentation for that. And then here we go in and this is an asynchronous call to d3.csv, gets our data. Actually, I just realized that I named the file the same thing as the function. So this is the data file, and that's the d3.csv function. We run the stratify that we just talked about, and then this is where we give it a sum, and optionally we do a sort as well. And if we don't sort, just so you can kind of have an idea of what it looks like, it just means I won't put the biggest ones on the top, and it's going to look, what did I miss here? Oh yeah, that's right, thanks. Yeah, it's kind of all over the place. Before we had the really nice big rectangles on the top, and it just orders it nicely. And then so we're associating, if you do a root.leaves, this is going to return an array of all of your leaves, because once we've done the data wrangling portion, where we now have an array for each one of these nested ones, we're just going to create one rectangle per element, right? So root.leaves is just an array of all of those boxes. Doesn't matter what the level is, because we have stored the depth. In other words, we've encoded the hierarchy of that tree inside each one of these data objects. So we associate that to these A elements, and they're A's because they're links back to the original documentation. And we append rectangles, and the width is a function of the data and all that fun stuff. Then, sorry, I'm kind of rushing through. These aren't even, I'm not a particularly big fan of tree maps anyway. But you can kind of go through and play with it to see how that changes. But once, I think that the thing that's most important before we get to the forest layouts is understanding how we're generating data, what we're appending this data to, and how are we getting the output SVG from that, okay? So the last part we're going to look at is these force-directed graph layouts, and I'm going to scroll. Let me see if I'm gonna. Yeah. So this is kind of the end result, and this is just like that tree was the quintessential D3 tree example. This is the most basic force layout example that you could possibly have. And in order to really understand what these forces are doing, I find the most effective way of doing that is by removing that and see what happens. Okay. So before I go into removing it, let's talk about what these forces are. Forces are functions that modify your position or velocity. That's it. A force puts your node somewhere with a certain velocity. And you can do all kinds of crazy stuff with it, because you can actually implement gravity and attraction and repulsion, or a mix of one of the two, and you can do some really cool stuff. There was a whole session on the D3 force layout at the conference that I was just at, and I have a link at the bottom of this, because he does some really cool stuff. He writes his own forces, and it can get really, really cool. But that's pretty much what it is. D3 has some standard forces, like the ones that we're going to look at, but remember, you can write your own. As long as it modifies the x, the y, the vx, and the vy, you can do really cool stuff with it, okay? So we're going to start here with a simulation, so it's called a D3.force simulation, and that really just starts it up, and then we're going to add 3 forces. These are the only 3 forces that come into play for this one here, okay? We have the link force, the charge force, and the center force. Now these names are already pretty intuitive, but to really get an understanding of what they do, we're going to take them out. One thing I want to note here is that these strings are anything you want. We call them names that are intuitive because later you can actually bring them back in and change them. But if you wanted to call it my favorite force, that's perfectly fine as well. The only thing that's kind of obviously hard coded is the name of the D3 function that returns that force. Okay? So, can anyone, just before I show you, guess, if we take out the force called force link, what is that animation going to look like? Just take a second to think about it, and then I'm going to show you. There is nothing holding them together, right? These other forces are acting on it, this force many body and this force center, which we're going to see what they do, but without the links, they just go all over the place. So the next thing we're going to do is, and I'll spare you the details of the syntax, you guys can go back. I really just want to make sure that I get to talk about what each one of these forces do, and this concept of adding forces together. So, force many body. So if I can make sure that I don't show you. Okay, so here we have the link force and the center force, but we don't have this force many body. Okay? What this force does, just because the name is not super intuitive, is it simulates gravity. And it can either do attraction if it's a positive number, or it can do repulsion if it's a negative number. Now, based on what you saw when we took out the link, is this a positive or a negative force that we've applied? When you took out the links that held them together, did they attract to each other, or did they kind of, right? So it's a negative force. It defaults, you'll notice that we never gave it a number, so it defaults with negative 30. That's if you don't give it any kind of strength. If you give it a number, then it will be proportional to that number. When we take out that force many body, what do you think is going to happen to our mass of nodes?
Stay there.
That's,
So we just stay there.
that's what happens. Okay, we take it out and it's not being pulled apart, and the links are bringing it together. Okay, so it's pretty unexciting, but that's what that force does. And the last one, as you can imagine, is called force center, and it forces your simulation to be at a certain point, in this case the center of your SVG. You take it out and it's nowhere near the center. Okay, so you can add these and play around with them, and you can come up with some really cool stuff. Another one that we don't use in this example that we're going to step through, but is pretty cool, is this idea of a force collide. What it does is it fakes, so imagine that around each node you have a bigger node that's invisible, and it's a bubble, and it doesn't let anything get within that bubble. So you pretty much just enforce this concept of a personal space to each one of your nodes. So if we just add that, and in this case it's the size, the radius of your circle is 50, that's what that looks like. So it looks kind of like a repulsion force, but it really is, it's more simpler. I'm not going to let anything within this radius collide with me. Okay? And that can be very useful when you have labels and things where you don't want them to be that crowded. Okay? And as I've implied continuously throughout this lecture, there is an endless number of forces and ways you can tweak them, and so this is like a class unto itself. You can also use specifically a force just on the x or the y. Maybe you don't care about both, so if you do these without force x, it really only cares about your x direction and your y direction. And another cool thing you can do is you can fix the position of your nodes. So here we fix the position of this node right here, and everything just wanders around it. Okay. So we're going to run through, and I'll run through the code instead of this, because this is just breaking it down and explaining it, which is you guys can go back and do later to see how easy it is to assemble these forces into something a little bit more complex. So you know the standard, widths and height, the SVG, we have a color that we're going to use so that we can actually color these nodes in. So here, we start a simulation, and then we add this first one, which is the force link. Okay, and then each link needs an ID, so this was the syntax terminology that I kind of glossed over earlier. So each one of our data points, we want to return the ID field so that we can identify these links later. Here we are going to add the charge force, and the charge right now is defaulting to minus 30, but just to play around with it, if we did minus 80, oops, that's not a 0. You can kind of see what that looks like. Actually, that's very, very similar. Probably need a bigger number. force. That's totally different. As you can tell, that's 800 and not 30. Oh, no, sorry, I totally messed that up. It's about strength. Let me go back here. So now they're really, really being pulled apart. Okay, and if you did a positive number in this case, they just come together because we're pulling it towards the center of gravity. Sorry for all the scrolling, I keep losing where I was. So yeah, so you can play with, it's a very simple modification of that force. And then here we have the force center, and obviously you need to tell where the center is. So we just do the math there, and we say, hey, get our width, our height divided by 2. So you could do a force center that's not actually in the center, and no one would know. It's any place, force it to center the node onto this point, the whole graph onto this x and y point that you give it. So here we're reading in the JSON file of the characters of Les Miserables, and we're creating a group for just the links, and this is something that I've mentioned before in homeworks, is if you want to make sure that one thing is beneath the other, just make sure you create that group in the DOM first, and then afterwards you can append to it whenever you'd like, but because that group comes before the other, it will render before the other as well. Here we're associating the links as a data to generate the lines, and we're appending lines and just actually making the width of the line proportional to the value of that data point. Same thing for circles. We're actually giving graph.nodes, which is an array of all the nodes to create the circles. We use the data to color it with that color scale that we defined earlier. And then we call this d3.drag, which is pretty cool. This is a D3 functionality, and it pretty much has these 3 endpoints: start, drag, and end. What do you want to do when the user does each one of these? And then we define them as functions called drag started, dragged, and drag end, which we define down here. So it will actually call these. So when you actually click on something, that's considered a drag start. So it calls the simulation. When you drag it, it updates the positions. And when you let it go, it kind of just bounces back. That's not something you get if you don't implement those 3 functions. Just make sure I don't rush through this. Here we're actually appending a title, and this was some homework back when there was a few questions that Alex answered on Slack about what was a title attribute. It's a cheap tooltip. It works. It's, my personal opinion, not the most aesthetically pleasing tooltip, but it works. And all you got to do is set the title attribute, and that way when you hover over something, you actually get the ID. And then we actually add, so we have that simulation, and we want to add the nodes to it. And we want to add the links to the force link. Notice that we add the nodes to the dot nodes of the simulation, but we add the links to the link force. Okay? The simulation does not require links. Because we want links, and they're only associated to a link force, this is where we add graph.links. So you can see it's a slightly different syntax. Simulation requires nodes, not links. And here is where we actually position things. A tick, as you might imagine, is the time increment every time the simulation updates itself. So when it updates itself, what do you want it to do? So this is where we put all of the code that will actually move things around. And all we really need to do here is we're not appending, we're not updating, we're not merging, we're just saying, hey, grab all of our links and put them in X and Y position, grab all of our nodes and put them in this CX and CY. So this is where we would have the update portion of our rendering code inside the on tick. And to finish it off, I just wanted to show you guys. So this is from the talk that the force layout workshop was on. Hopefully this loads. So this guy, his blocks and his GitHub has all kinds of stuff. And he generates forces, then he gives you this little slider, right? So this is where the strength is 0. Then if you increase the strength, they start attracting themselves to each other, but they also have this magnetic force that repels them. So you can kind of see what it does, and you can go a little crazy with how strong that is. And the opposite, if the strength is negative, is they repel each other, so eventually they just all end up trying to avoid each other while still being attracted outwards. So he has all kinds of these cool things that you can play. He actually has a few, I don't know if they're JS fiddles or something, where you change and add forces, and you can see how that actually reflects on the final set of points. So, you know, it's a cool toolbox kind of thing. Cool, like, playground. And that is it for layouts. Sorry we rushed a little bit towards the end. I do recommend, if you want to get more familiar with them, to just change parameters, play around, and of course read the documentation, which is really, really good. And are there any questions? We have 2 full minutes. If not, I guess I'll see you guys at Homework Lab tomorrow at 6, and